Okay, so let's start. Any questions from last class? Yes. Yes. I posted on Google Classroom, but I use the term strongly convex to refer to the case when f of alpha x plus 1 minus alpha y is strictly greater than alpha, so strictly less than alpha times f of x plus 1 minus alpha f of y. This is what is called strictly convex and not strongly convex. There's a different notion called strongly convex, where you want something a little more than this. Right? So that's point number one. The second point is that so we also use the second derivative test, right? So a function is convex if and only if the second derivative is if it's non-negative, right? It's an if and only if condition. However, when it comes to strict convexity, the function is strictly convex if the second derivative is strictly greater than 0. But if the function, if the second derivative is 0 at some point, right, it does not mean that the function is not strictly convex. There can be functions for which the second derivative is equal to 0 for some point and greater than 0 for all other points, but the function can still be strictly convex. Right? So sufficient condition, the second derivative test is a sufficient condition for strict convexity. However, for convexity, it is a necessary and sufficient condition. Right? For example, if you take the function x to the 4, right? This is a strictly convex function, but the second derivative is equal to 0 at one point. Which point? 0. At x equal to 0, the second derivative is equal to 0. Okay? So that's one point to keep in mind. Okay? Any other questions? Y equal to x square, the second derivative is what? It's always positive. Any other questions? Any other questions? Okay, so let's continue. Today we'll switch from calculus to matrix theory and linear algebra. Again, this is going to be, some part of this is going to be a refresher on what you've seen in the matrix theory course, but we'll go beyond that pretty soon. Okay, so very quickly, let's just recap some basic definitions. Right, so what is the vector space? Right, the vector space is some non-empty set V equipped with some operations. Right, so a vector space is always defined over a field. The field, typically we take this to be the set of real numbers. Right, and over this set V, we define two operations: vector addition, which lets you add two vectors, and scalar multiplication, which lets you scale a vector by a scalar. Right? The scalar in this case will be a field, or actually it is typically chosen to be R. And the set forms a vector space if certain properties are satisfied. Right? In particular, vector addition is commutative. It is also associative. There exists an identity element, right? An additive identity, such that you can add this additive identity to any vector and it gives you back the same original vector. Right? This is what we call the zero vector. And we also have an additive inverse, which means that for every vector, I can find some other vector, such that if I add the two together, I get the zero vector. And scalar multiplication is associative in the sense that if I multiply a vector by a product of two scalars, then it's the same as first multiplying one of the scalars with the vector and then multiplying that later. So in other words, the order in which you add or the order in which you multiply doesn't really matter. Right? And another property is that multiplying by 1, the scalar identity, and the scalar multiplicative identity, does not change the length of the vector. Alright? And addition, the scalar addition also distributes over, or in other words, you also have a distributive property which says that alpha times alpha plus beta, if I add two scalars and multiply by a vector, then it's the same as multiplying the first scalar by the vector and then multiplying the second scalar by the vector. Also, alpha times v1 plus v2 is equal to alpha times v1 plus alpha times v2. These are basic properties which hopefully you've seen in your linear algebra course. Okay, and with this you will also be able to answer the following questions. So, what is the subspace of a vector space?
Any subset that is adjacent to the
Correct. Any subset of a vector space, which is also a vector space in its own right, is a subspace. Now, if I give a vector space, an arbitrary set and some particular field, then you have to basically test whether all those properties are satisfied to check whether it's a vector space or not. Now, if I give you a subset of a vector space, and you want to know whether this set is a vector space or not, whether it's a vector subspace or not, then you have to check all the 7 properties. What is sufficient? Just 0? Yeah, so in particular, basically if it is closed under all linear combinations, then it's also a vector subspace. Correct? So closure under linear combinations, it's enough to just check that. Okay. And what do you mean by linearly independent vectors? Okay, so a set of vectors is linearly independent, or linearly independent if no vector in that set can be written as a linear combination of any of the other vectors. Right? Or another way to put this is that, so if I give you vectors v1 up to vn, then v1 through vn are linearly independent if alpha 1 v1 plus alpha 2 v2 and so on plus alpha n vn, this is equal to the 0 vector if and only if all the alpha i's are equal to 0. Right? If you take any non-zero linear combination or non-trivial linear combination of the vectors, then it's never going to give you the 0 vector. Okay? Okay, good. What do you mean by the span of a given set of vectors? The set of all possible linear combinations of the vectors is called the span of the vectors, and this forms a vector space. Right? And this is called the subspace spanned by those particular vectors. Okay, so and for a given vector space, any set of vectors for which the span is equal to the vector space is called a spanning set for that particular space. Right? And okay, so we already said when vectors are said to be linearly independent, what is the basis of the vector space? Okay, so basically any linearly independent spanning set for a vector space is called a basis. So basically a basis is a set of vectors which satisfies 2 properties. It spans your vector space, and secondly, they are linearly independent. Alright, so for a given vector space, is the basis unique? You can find multiple bases for a given vector space. What is the dimension of the vector space? Right, so the size of the basis is basically the dimension. So even though the basis for a vector space is not unique, even though there can be multiple bases for the same vector space, the number of vectors in any given basis is always going to be the same. Right? And that is what we call the dimension of a vector space. Okay, and in your matrix theory course, you would have seen different vector spaces which are associated with a given matrix. Right? And in particular, you would have seen 4 fundamental subspaces of a vector space or corresponding to a matrix. What are they? Yeah, so there are 2 null spaces, the right null space and the left null space. So what is the row space? The span of the row vectors. Column space is the span of the column vectors. What is the right null space? So, or put slightly differently, for example, it is basically the set of all vectors which are orthogonal to the rows of, or the orthogonal complement of the row space, right? And what is the rank of a matrix? Yeah, dimension of the column space. What is the dimension of the row space going to be equal to? We say, right? Okay, and what is the nullity? Okay, equivalent. Yeah, one at a time perhaps. So, of course, the nullity by definition is equal to the dimension of the null space, the right null space. And what is it equal to in terms of the rank? The number of columns minus the rank of the matrix. Right? Okay, and in other words, the rank nullity theorem says that the sum of the rank plus the nullity is equal to the number of columns. Right? Okay. And suppose I give you an arbitrary matrix and I ask you to compute the rank or the nullity for that matter. How would you compute this? Alright, so basically with the Gaussian elimination, bring it down to row echelon form, and then you count the number of pivots, right, or the number of non-zero diagonal entries, and that gives you the rank of the matrix. Okay, so what would be the computational complexity of doing so? How many arithmetic operations are required? So order NQ. Okay, so hopefully you know what elementary row operations are. How do you convert a matrix to the row reduced echelon form or the row echelon form, and basically how do you write this as a QR decomposition, right? You can write any given matrix as a product of an orthogonal matrix times an octotriangular matrix. Okay. Okay, so now that we have all our definitions sorted out, let's just check which of the following are vector spaces. Right? Just some quick exercises to see. So, given any field, right, the set of all vectors with elements from that field, is it a vector space over the field? It is, right? So, for example, Rn is a vector space over R. Okay, what about the set of all m by n matrices with elements from R? Yes? Anyone saying no? Or anyone doubtful? Okay, is it a vector space? I don't see a resounding, I don't hear a resounding yes. So yes, the set of all m by n matrices with elements from R. How can you say that it is a vector space? Okay, why are the rest not convinced that it's a vector space? If I add two m by n matrices, what do I get? Another m by n matrix with elements from R. Right? Is addition commutative? It is. Addition of two matrices is commutative. Is it associated? Yes. Does there exist a zero vector? What is it? is the zero matrix, right? And does the additive inverse exist? So if A is a matrix and minus A is its additive inverse. What about scalar multiplication? Is it associative? It is. Is it distributive? Yes. If I multiply 1 with a matrix, what do I get? The matrix itself, right? So it satisfies all the properties of a vector space. Right? So it is a vector space. What is the dimension of this vector space? It's mn. Right? So in order to say that the rank that the rank is equal to something, or in order to say that the dimension of this vector space is something, again remember, do not confuse this with the row space or the column space of the matrix. We are looking at the set of all possible m by n matrices, not a given matrix, and asking if this set is a vector space. Correct? So in order to do this, I need to provide a basis, right? So can you give me a basis for the set of all n by n matrices? Right, so I can define a matrix A by J, which is 0 everywhere else except the I comma j entry. Right, so it's 0 everywhere except 1 in the I comma j entry. Right? These AIJs are all linearly independent. Do you agree? Yes. And they span the set of all m by n matrices. Yes. Because I can write any matrix B as Bij times A, the matrix Aij. Correct? So you all agree that this forms a vector space. And what is the dimension? N into n. Okay, great. So in other words, we are in some sense similar to Rmn. Right? It's just that I reiterate it out in a different order. I write the entries in a different order. Instead of writing it as a column matrix, instead of writing it as an n by 1 matrix, I choose to write it as an n by n matrix. Right? They're all isometric. Okay. What about the set of all rational numbers or set of all vectors with rational entries over the field R? Why is it not a vector space?
Take square from R. Take square from R. Square.
Okay. Okay, root 2 from R.
I take one some once.
So this is not a vector space because multiplication itself, it's not closed under multiplication. Right? For example, root 2 times V is not in Qn for any non-zero. Right? Any questions? Yeah,
It is also set of extra numbers.
it is a vector space. Yes. So that is why the field and the set, the set of vectors do matter, right? Depending on how you choose things. Any questions? Okay. What about the set of all polynomials of degree less than or equal to 3 with coefficients from R? It is. And what is the dimension of this vector space? 4, right? Because I can write any polynomial as a0 plus a1x plus a2x squared plus a3x cubed. And what is the basis for this vector space? Right, so 1x x squared x cubed. These are elements from the set of polynomials. We treat them as vectors. But of course, we can verify that this set satisfies all the 7 properties of a vector space. Right? Good. What about the set of all possible polynomials with coefficients from R? Is it a vector space? It is a vector space. It will satisfy all the 7 properties. What is the dimension of this vector space? It's an infinite dimensional vector space. Okay. What about the set of all continuous functions in over R? Is this a vector space? Yes? Why not? Okay. Yes. Okay, does it satisfy all the 7 properties? First of all, is it closed? To take the sum of 2 convex functions, sorry, 2 continuous functions, it's going to be a continuous function. Take any linear combination of continuous functions, it's going to be a continuous function. Right? Is it commutative? It's addition over continuous functions. So f of x1, f1 of x plus f2 of x is the same as f2 of x plus f1 of x. Right? Is it associative? Is addition of functions associative? It is. What are the other properties that we have to check? What is the zero? What is the identity element? Zero. It's a zero function. Right? So the identity is zero is basically f of x equal to 0 for all x. Right? So that's the additive identity. What is the additive inverse? It is the negative, right? Minus f of x. What about scalar multiplication? Multiplication by continuous functions. Again, it's associative, it is distributive, and it's also closed. Right? So this is indeed a vector space. What is the dimension of this vector space? Infinite. But is there a difference from the previous example? Yes or no? No, forget about subset. Yeah. What is the subset of what? Correct. So the set of all polynomials is within the set of all continuous functions. Correct. But now are the two the same? Then yes.
Take in this space.
Yes.
That will convert to that space. That's incomplete.
Correct.
This is complete.
This is complete. Yes. Okay.
Long existing that is
Correct, it is not, right? But in some sense, you can always approximate. So you can approximate any continuous function by a polynomial, but you cannot write it as a polynomial. So you can write it as a sequence of polynomials which can converge to the continuous function. So this is a much bigger space than the set of all polynomials. Alright? Okay, so here's one more example. Let me take okay, how do you say that it is uncountably infinite? So the first one is countably infinite, that is clear. Right? The set of all monomials forms a basis for the set of all possible polynomials.
like a long question, but how do we even start defining the basis for
for the set of all continuous functions. Okay. So again, if so, then what in some sense, what is the basis? What is the basis for a given vector space, right? So it's a basis if you can write any function. So basis could be an uncountable set potentially, right? So firstly, all vectors have to be linearly independent. So essentially, you take any subset, any finite subset of these vectors, it will be linearly independent. That's point number one.
One question: if A to X and E to the power 2x, like are they linearly independent?
Can you write e to the 2x as some constant times e to the x? What? You can't. Right? So they are linearly independent. So that's number one, they have to be linearly independent. Secondly, they have to span the space. So in this sense, what is meant by span? You should be able to write any vector as a linear combination of finitely many vectors in your basis. Okay. So if this is possible, then that forms the basis.
Let's say your continuous function has parameters in between. So let's say for x is 0 c to the power x, from 0 to 1 is probably some linear function, and then after that it goes some cubic function.
Okay.
How does that get off is the basis?
I'm sorry, I don't understand what this. I'm not presenting a basis for the set of all continuous functions. So what we gave was a continuous function, right? So what was the question?
So how do you include parameters into the basis? Let's say it's like e to the power x from 0 to 0.
Correct.
How do you?
So you can add that to the basis if you wish. Correct.
But then it has to be e to the power x from so just so the actual be from 0 to infinity will be 0, right? But that yes.
No, I don't say that. Okay, so what you're asking is,
Okay.
so you take a function which is 0 for x less than 0. Let's take a function, and it is, okay, it's straightforward, which is equal to x for x greater than 0. Right? No, again, you can't write this as a sum of two polynomials, for example, right? Or any finite number of polynomials. Correct? So obviously you need a more complicated basis to represent this set of functions. It's not clear what the basis should be. It's certainly not the set of all monomials or the set of all polynomials. That's simple.
Polynomial exactly approximate from the base vectors.
Yes.
But in case of continuous functions, you need an identity to make to any given vectors.
That's why I'm not given presented a basis for the set of all continuous functions.
Even there is a basis. You cannot for any.
That's the definition of a basis. You should be able to write it as a finite linear combination of basis vectors.
And there is a basis for polynomial.
No, for polynomials it is straightforward, right? It's a continuous function.
Not only identity. Imagine
Generally it is, again, this one? Yes.
It's super.
You want to write sin x as what? Why? Sin x as what? What is your basis? Okay, let's look at one last. Any questions? Okay, so let's look at one more example. The set of all real numbers, but now the field is the set of all rational numbers. the set is the set of all real numbers. The field is the set of all rational numbers. Is this a vector space? Yes. How many say yes? It is a vector space. How many say no, it is not a vector space? Okay, again, what about the rest? Does it satisfy the certain properties? Is addition commutative? It's associative. Second, the set of real numbers, right? It's closed under whatever multiplication. So, yeah, any questions? Yeah, we'll come to that. Listen. So, okay, are all these properties basically satisfied? Commutative, associative, the zero element, it's just the real number 0. What about additive identity, additive inverse? Yes, so negative numbers are there in the set of reals. Again, if I take alpha, beta from rational numbers, this property is satisfied. 1 times any real number is equal to the real number itself. It's distributed, right? So it forms a vector space. Right? Does everyone agree? Okay. So this is a vector space. What is its dimension? It's just R. Just take R. Dimension is 1. When you write every real number as a scalar multiple of one of the elements from R. Yeah, so how many? So is it finite? First question, is the basis for R finite? Right? You cannot write every real number as a finite linear, as a linear combination of finitely many elements from R. No matter which basis you pick any set of, say, real numbers, right? So a set of all linear combinations with coefficients from the set of rationals, with rational coefficients, it doesn't get you to a set of all possible real numbers. Right? Okay. So then, for example, let's take root 2, root 3, root 5, root 7. Basically, take whatever the set of, take all possible primes, take the square root of all those primes. You can root 6. Sure. Anything. I just need to demonstrate one thing. Okay, so it is infinite. Is it countably infinite or is it uncountably? And why? Yeah? Yes. So basically you take most rational numbers, take the square root, take the cube root. These in general will be linearly independent. You take now, again, this is not enough, right? You also have a set of transcendental numbers, pi, e, and so on. Right? So this is an example of an uncountably infinite dimensional vector space. Alright? But again, for most part, we'll be interested in Rn. Right? That's the vector space that Rn or Rn. We will mostly be interested in finite dimensional vector spaces, but you should know the difference, right? What is an infinite dimensional vector space? Because many of the tools or many of the techniques that we develop for finite dimensional vector spaces don't always extend to infinite dimensional vector spaces. Okay. Yeah, the advantage in working with finite dimensional vector spaces is that you can always write them as, you can represent any vector as an n by 1 matrix, what I call a column vector. Alright? For example, the vector space could be a set of all possible polynomials of degree less than or equal to 3. Right? But I can write any element, I can represent this as a vector of length. Okay? And all operations, all vector operations can be just done as though you're doing it on column vectors. Right? So basically, if you take any finite dimensional vector space over R with dimension n, it's essentially isomorphic to Rn. I can just work with Rn without worrying about exactly what vector space I'm working with. The other structure doesn't matter. Right? So for example, again coming back to the example of polynomials, polynomials have some additional properties. But that doesn't really matter as long as you're doing vector space operations. I can treat them as Rn. Right? And whenever you write vectors in terms of, say, column vectors, underlying this you are representing things in terms of some basis. Well, typically when you look at Rn, you are looking at the standard order basis. Right? And similarly, again, when you're working with finite dimensional vector spaces, if you have any linear transformation, you can represent it as a matrix. Correct? So any linear transformation from Rn to Rn can be written as an m by n matrix with real entries. So these are things that you would have definitely seen and should be very comfortable with. Another notion you would have seen in your matrix theory course is the notion of similarity. So we give you two matrices, let's say n by n matrices, A and B. When are they said to be similar to each other?
Matrix like A equal to S inverse A, X.
Yeah. So we say that the matrix A is similar to another matrix B if we can find an invertible So if we can find an invertible matrix P such that, say, I can write A as, say, P A P inverse or P inverse A P. So P inverse A P. Right. So if I can find an invertible P such that A can be written as P B P inverse, then I say that A and B are similar to each other. Right? Have you seen this definition before? Hopefully yes. Right? And what does similarity essentially do? What is the geometric interpretation or the linear algebraic interpretation of similarity? It's just a change of basis. Right? So originally I have a linear transformation which can be represented by a matrix A. Right? Now if I change the basis, right, then what exactly is happening? So for example, if I have a vector space with a particular basis, let's take the standard order basis. Now let's say I decide to write all the vectors in terms of a different basis. For whatever reason, maybe it's more convenient to work with. Right? So I give you some basis, V1, V2 up to Vn. So I present your basis and I give you a vector, let's call it W. So the vector W is represented with respect to the standard order basis. And I want to write W now in terms of the new basis. Okay. Then what would be the representation equal to?
Matrix of all the E's, one side is W.
Okay, and how do you get that?
Like we already basically that we have W in the standard basis. So
Correct.
for each of the elements of the basis, we translate them or sort of transform them according to the basis that we want.
Yeah. So basically, what you want to do is write W as some linear combination of v1, v2 up to vn. Right? The coefficients of the vi's are basically going to be the elements of the vector in the new basis. Right? So if I can write w as, let's say, alpha 1, v1 plus alpha 2, v2, and so on. What is the representation of w in terms of the new basis? It is just going to be alpha 1, alpha 2, and so on. So this vector is basically the representation of the same vector, but now in terms of the new basis. Right, so this is our basis. Correct? So basically, I've given you the view, I've given you all the vectors in the basis. How do you find the alpha i's? We just solve the system of linear equations. Right? So W again is a vector, and so it's a column vector. Represented in terms of the standard ordered basis. Okay, so W is basically, you take the matrix V1, V2 up to Vn times the vector alpha. Okay? It's just the same thing. Correct? So what is alpha equal to? So in terms of the new basis representation for the same vector W would just be P inverse times W, where this matrix is what I call P. Right? So essentially, multiplication by any invertible matrix is basically equivalent to a change of basis. Right? So multiplication by an invertible matrix is equivalent to a change of basis. Okay? Any questions? Okay, so now what is similarity in terms of change of basis? So if I take any vector x, right, I want to know what is A times x. Correct? I'm saying that A is equal to P times B times P inverse for some invertible matrix P. So effectively, what am I doing? P times B times P inverse times x. Right? What is P inverse x? Correct. It is the vector x, but in terms of a new basis. Right? Yes, sir? And we is basically the representation of x in terms of a new basis, which is just the columns of P. Right? So my new basis is basically the columns of P, and P inverse x will be the representation of x in terms of this new basis. And I have this, right? So I multiply by B, so it's basically the same. I'm doing some linear transformation, and then again multiplying by P. So what is multiplication of by P equivalent to? Reverting back to the old basis. Right? So in other words, I have a matrix A which represents a linear transformation, maybe in terms of the standard ordered basis. The matrix B is effectively the same linear transformation, but now it is represented in terms of this new basis, which is the columns of P. Right? So any two similar matrices, that is why you call these matrices similar. Right? Because effectively you're effecting the same linear transformation, but you're all doing this in terms of a different basis. Right? Great. So and a lot of the basic course of linear algebra we discuss diagonalizability, wherein you want to know if your given matrix is diagonal in some basis. Right? Is your matrix similar to a diagonal matrix? Right? So matrix is diagonalizable if it is similar to a diagonal matrix. Or in other words, there exists some basis such that this linear transformation presented to you is diagonal in that particular basis. Right? So that's the geometric representation of similarity and diagonalizability. Great. But of course, we'll get to diagonalizability in a little bit. But before that, I mean, when we talk about eigenvalues and eigenvectors, let's discuss another basic quantity for matrices, right? And that is the determinant of a matrix. So what are the different definitions of determinant that you've seen before? Sorry?
Just backwards the period of change the unit.
Why would you say that? Okay.
We have a unit, say, height of unit.
Okay.
So the standard basis.
Okay.
And the linear transform change that into the parallel.
Correct.
And the factor of change itself determinant.
Right. So the volume of the parallel is going to be used as that's sort of a geometric interpretation of the determinant. But given a matrix A, how do you define the determinant of the matrix A?
See, I don't think AI or sigma.
Has everyone seen this definition before? Some or all possible permutations of something. Some of you say yes. How many of you have seen it before? Okay, how many of you have not seen it before? Okay, fine. At least some of you have not. Fine. So let's go over that definition first, because it's a more, you can still get a sort of closed form expression for the determinant. Right? So let's first discuss what a permutation is. Given the set of first n positive integers, 1, 2, 3 up to n, a permutation is basically a rearrangement of this set. For example, I take 1, 2, 3, 4. Any rearrangement of 1, 2, 3, 4 is a valid permutation. So for example, 3, 1, 2, 4 is a permutation of 1, 2, 3, 4. And this permutation, sigma of I, is basically the element that it is permuted to. So sigma of 1 is equal to 3, sigma of 2 is equal to 1, and so on. It's just any bijective map from 1, 2, 3 up to n to 1, 2, 3 up to n is a permutation. Right? Okay. So how many permutations are there for 1, 2, 3 up to n? N factorial permutations. Right? There are n factorial possible permutations. Great. Now, given any permutation, right, I can bring this permutation back to 1, 2, 3, 4 by sort of rearranging the elements. And let's look at the rearrangement wherein I'm only allowed to make pairwise exchanges. Okay? So, for example, suppose I give you this permutation 2, 1, 4, 3. I can convert 2, 1, 4, 3 to 1, 2, 4, 3, and then to 1, 2, 3, 4. So basically I swap 1 and 2, and then the second step I swap 3 and 4. Right? And I could bring this down back to 1, 2, 3, 4. Any questions? Is this clear? Okay. And I found the number of such operations required. Okay. in this case, I require two pairwise exchanges to bring this permutation back to 1, 2, 3, 4. Alright? Okay. But then the number of operations required to bring it down to 1, 2, 3, 4 is not unique. Right? For example, I have 2 and 4, 3. 1, 4, 3. I could first do 1, 2, 4, 3, and then I could have done 1, 2, 1, 4, 2, 3, and then maybe done 1, 4, 3, 2, and then done 1, 2, 3, 4. It's a valid sequence of pairwise exchanges, and again I've come down from 2, 1, 4, 3 to 1, 2, 3, 4. Right? So even though the number of pairwise exchanges required to bring a given permutation to 1, 2, 3, 4 is not unique, one thing is that the parity is always the same. The number of operations is either always odd or it's always even for a given permutation. Okay? So the number of pairwise exchanges required to go from any permutation back to the correct order, 1, 2, 3 up to n, the increasing order, it's always either going to be odd for that permutation or it's going to be even. And I will call the sign of a given permutation to be +1 if the number of pairwise exchanges is always going to be even, and -1 if it is always going to be odd. Okay? That makes sense? Again, I'm not proving all of this, but just take it as a fact. Okay? You can for example, take any permutation you want, and then try to find how many pairwise exchanges are required, and you always it's always odd or it's always even. Okay? So you can define the determinant of a matrix in the following way. So I define this quantity for a given matrix, and the summation over all possible permutations of quantity up to n, there are n factorial of them, remember, of -1 raised to the sign of that permutation times a1 sigma of 1, a2 sigma of 2, a3 sigma of 3, up to an sigma of n. Alright, so this is how I define the determinant of a matrix. Alright? Great. So let's take a quick example. Suppose I take a 2 by 2 matrix. What are all the possible permutations of, there are 2 elements, right? So it's a 2 by 2 matrix, so n is equal to 2. What are the possible permutations of 1, 2? So the permutations are 1, 2, the identity permutation, and 2, 1. These are the only 2 possible permutations. What is the sign of 1, 2? That's one. The sign of this is -1. Sorry, I should have maybe done this a bit differently. Let me just say sign of sigma times this. Because we have defined it, so it's either +1 or -1. Okay. Alright, so what will the determinant of A be equal to? Alright, so let's again just pick this definition. So I have 2 terms in the determinant. The first permutation is just 1, 2, and that is +1 times a1 sigma of 1. What is sigma of 1? I'm taking this permutation first. Right, so it is a1 sigma of 1, which is a11, times a2 sigma of 2, which is a22, because sigma of 2 is equal to 2. The second permutation is 2, 1. So what do I find in this permutation? It is minus 1. A1 sigma of 1, which is A12, times A2 sigma of 2, which is A2, which is just A11, A22, minus A12, A2. This is what you would have seen in your high school. Right? So similarly, you can verify this for a 3 by 3 matrix, and so we'll effectively get the same. Right? So another expression or another way to compute the determinant that you would have seen is in terms of the cofactors. Right? So what is the cofactor of a particular element in the matrix? Yeah, so the cofactor of the ijth element is minus 1 raised to I plus j times the minor, which is basically the determinant obtained by deleting the ith row and jth column. Correct? And you can write the determinant in terms of the cofactor expansion. Right? Either you can expand in terms of a row or in terms of a particular column. Right? But both of these, when you look at the number of operations, arithmetic operations required to calculate the determinant, what is it going to be? How many operations are required in this case? Is it polynomial? So this is my definition of the determinant. Suppose I want to compute the determinant using this approach. It's a brute force approach. Right? N factorial, right? So this is huge. It's not, is N factorial polynomial in N? It is not, right? It goes to play like N raised to the N. What about this particular approach? Is it any helpful? Not really, right? So both these approaches are not computationally efficient. Is there a more computationally efficient way to compute the determinant of a matrix? What is it? Okay. Have you seen a computationally, at least a more computationally efficient way of computing the determinant of a matrix? Yeah? Okay, what if it is not diagonalizable? Okay, great. How do you find the eigenvalues of a matrix? To find the eigenvalues, you need to solve the determinant equation, right? In which case, you have to compute the determinant. So, okay, how do you do singular variable decomposition? So does it mean that you can't compute the determinant, let's say in polynomial time? Okay. So you've not seen any other way to compute the determinant other than these two approaches? Yeah? Yes. Okay, will you do it using the echelon form? Have you seen computing the determinant from the echelon form? Yes, have you seen it before? Have you not seen it before? Okay, so okay, all right. So let's see, there are three types of row operations, right? To bring any matrix down to the row reduced echelon form. What are the three types of operations? So let's take each of those one by one. Suppose I scale one row of a matrix by some constant. What happens to the determinant? It gets scaled by the same amount. Suppose what is the second type of operation? Okay, exchange row exchange. If I exchange two rows, what happens to the determinant? The sign changes. So what's the third one? Fine, let's split it into two. So basically you subtract one row from another row. Right? Or whatever. Row 3 minus 2 times row 1 or something. right? So what happens to the determinant if you do that? There is no change. Right? So that already gives you, and what is, once you bring it down to the row reduced echelon form, what is the determinant of that matrix? It's diagonal. Well, again, if you bring it down to the row reduced echelon form, it's always identity. Right? So the determinant of that matrix will be either 1 or 0. Okay? Because either it's full rank or it is not full rank. If it is full rank, then the row reduced echelon form will give you an identity matrix. Otherwise, it's going to give you the determinant of that matrix is going to be 0. Okay. So that gives you an efficient algorithm, right? Because bringing it down Gaussian elimination is very efficient. Okay. So what is the procedure? You bring the matrix down to the row reduced echelon form. And let's say you keep track of all the row multipliers that you had and the number of row exchanges. Right? So what would the determinant of A be equal to? -1 to the power beta. So -1 to the power beta. Yeah, into all the multipliers. It's very careful over here. Is it? Yeah? Yeah. Correct. So 1 by the product of the multipliers. Right? Because the determinant of the reduced form would be equal to -1 raised to beta times alpha 1, alpha 2, up to alpha k. Correct. But that is 1. Or 0. Correct. Correct. Yeah. So let's let me call it. Okay. So, what is the computational complexity of computing the determinant? What are you doing? Alright, so any questions so far? Okay.